Okay. Last lecture we had seen about the counter. What do you mean by the counter? As we had seen, the counter has many applications. It can able to measure a frequency. It can able to measure a time. It can able to measure a different clock pulses. So here one of the example of an counter. What we had seen in the last lecture. So this is the conveyor belt on which the boxes are moving, and this is the light source from, and this is the light detector, and this is what we call a counter. When this box passes, this light will get cut, and due to that the counter will increase. So you can able to find how many number of boxes are that passes from the conveyor belt. What is another application? You know about the digital clock we have. So this is the example of a digital clock, correct? So we can able to use the counter in that application also, and here to find the number of person had been passed through the gate. So again, in the gate you just put the light source and the photo detector. When the person moves from this door to that side, the lights will cut, and due to that the number of person entering to the room will be counted. So there are the two types of counters we have. We call the synchronous counter and the asynchronous counter. I'd asked you the question in the last lecture, which is the synchronous counter and which is the asynchronous counter? How will you identify the synchronous counter? Let us take the example of synchronous. So look at this clock pulse. It has been given common to each and every flip-flop. That means whenever there is a change in a clock pulse, all the flip-flops, the output will change at a time. That's why we call it a synchronous counter. What about this? Why we call it asynchronous counter? Look at here. The clock had been given to only one flip-flop. Rest of that flip-flop, the output of this flip-flop had been given to the clock to another flip-flop. Again, the output of this had been given to the input of this flip-flop. So that's why this is called asynchronous flip-flop. So if you look at the difference between synchronous and asynchronous, synchronous counter, same clock, they have the different flip-flops, the different clock. So it is a faster, it is a lower bit, not faster compared to the synchronous, but the design is much more complex because each and every clock pulse with the same time you need to send it to the each and every module. So you require a in terms of a hierarchy such a way that each clock goes to the millions of gates at the same time. So that's why it makes complex circuits. So design is relatively easy because the clock doesn't depends upon the flip-flop depends upon the clock source. It depends upon the different inputs. So decoding error not present here. In this decoding error are present. So any required sequence can be designed. That means sequence means if you are going to design a sequence of 0, 1, 2, 3, 4, 5, 6, and someone asks you to design, okay, I don't want 0, 1, 2, 3, 4, 5, 6. I want to design 0, 2, 4, 6, and again 0, 2, 4, 6, 0, 2, 4, 6. Such sequence is required. So in synchronous it is possible to design such sequence, but in the asynchronous only fixed sequence are been possible. That means 0, 1, 2, 3, 4, 5, 6 only is possible. If you want to design a 2, 4, 6, 8 sequence, it's not possible. Okay, so this was the difference between a synchronous and asynchronous counter. Here I took an example of an 2-bit ripple counter that should be -8, and that we are going to design using the JK flip-flop. Now what do you mean by, first of all, -8, and what do you mean by the JK flip-flop? See, you know the table. When both the J and K are 0, 0, there should be no change. That means the previous state should remain as it is at the next state. When the J is 0, K is 1, it should always be in the reset mode. That means what might be the previous state, it always remains to the 0. When J is equal to 1 and K equal to 0, the output of next state, it always remains to the set state. Set means it always remains to the 1. What might be the present state? But what is the important over here? When both are 1, J and K, it will work in the toggle state. And I told you what do you mean by the toggle state? It's a complement of the previous state. If the previous state is 0, it will give the output of the next state that will be 1. If the previous state is 1, output of the next state will be 0. So that's what the difference we need to understood. And we are going to design a 2-bit ripple counter. Okay, that is up counter. Now, what do you mean by the -8? First of all, that means output of the flip-flop take the changes on this negative edge of trigger. That's why we call it a negative edge trigger. Now, I have two flip-flops over here. Which will be the negative edge and which will be the positive edge of trigger? How will I identify whether it's a negative edge or positive edge of trigger? Look at the clock source. That means here if I apply 1 directly to this clock source, this flip-flop will work. That means 1. That means this flip-flop works on a positive edge. That means it required. So which is the possibility to get it 1? When the transaction takes place from 0 to 1. That means this is the positive edge of trigger. Now what I had added? I have added a bubble over here. That means this flip-flops will work on a zero logic. How will get the zero logic? That means the transaction must takes place from 1 to 0. That's why we call as a negative edge trigger. Are you getting or not? That means if I give the 0 not, then only I will get a 1 over here. That means how you will get the 0? I will get a 0. That means you need to transaction takes place from 1 to 0. That's why this is a negative edge trigger. Here there is no bubble. That means if you will give 1, this flip-flop will change the state. How will get a 1? There is only one possibility to go from 0 to 1. That means it's a positive edge of trigger. Okay, I hope everyone got this point because there is very much important about this. Okay, don't need to mug up the things, just understand the things, that's all. So you need to design a up counter. What do you mean by the up counter? The sequence starts with a 0, 1, 2 and 3. Why 3 till? Because it's 2 bit. That means 0, 0, 0, 1, 1, 0 and 1, 1 possibly. Again, when you reach to the third state, it should not be stopped. That means it should be in the continuous format. That's why this table had been shown over here in a loop. So it's a 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. That is an up counter. Now, how to design this up counter? It's a 2 bit. So we must require a 2 flip flop. And which flip flop I had used? The JK flip flop. Look at the JK flip flop. Where I had connected both the inputs, I had connected both the inputs to the 1. That means if you know the JK flip flop, if both the inputs are 1, that means it will work in a toggle mode. That means present state will convert into a next state with a toggle mode. Okay. Now look at over here, whether it's a synchronous or asynchronous. With the asynchronous. Why? The clock has been given over here in the first flip flop only. What about the clock in the next flip flop? That is the output of first flip flop. That means it's a negative edge. That means JK flip flop change its states when clock takes places from 1 to 0. Where are in each flip flop flops had been given. So look at the flip flop 1. When this state changes, when state changes from clock input changes from 1 to 0. Understand flip flop 1. Why? Because it change its states. Why it change its states? Because the J and K are connected to the 1. So clock, when take the transaction from 1 to 0, Q1 will be in change. Now what about the flip flop 2? The clock is connected to the Q1. That means I can say that your flip flop 2 change its state. That means Q2 changes when not a clock, the Q1 changes from 1 to 0. Understand this thing. Okay, this is very much important. The first flip flop, why the clock changes? Because clock is connected. When the flip flop 2, clock is connected to the Q1. So Q1 changes states from 1 to 0. At that time only you can able to change its state. Q2 change its states from present state to the next state. Know about this, the JK, and both are 1, it works in a toggle mode. That means present state will change to the next state in terms of complement. Now, at initial state of the first clock pulse, both the states are 0, 0. That means Q2 and Q1 both are 0, 0. At the first clock pulse comes, that means here negative edge clock pulse comes. What happens to this change? Q1 changes from previously. What is the state we have? Present state we have 0. Now due to the J and K both are 1, Q1 will change its state from 0 to 1. Now again, the Q1 changes states from 0 to 1. That means flip flop 2 will not change its state, because to change the state of a Q2, Q1 should go from 1 to 0, and that is not possible over here. The QH1 changes from 1 to 0. So this state will remain 0 to 1. Okay, so this state remains as it is. There is no change in the state. Okay, so that means now this state will come over here. Why? Because that is a present state. So that will be a present state. Okay. Now look at over here. At the first clock pulse, This is the present state. I had put it over here. Now at this clock pulse, this one, look at this. Again the J and K are connected to 1. The present state of Q1 is 1. Present state of Q1 is 1. So at this clock pulse, this 1 will change to 0. Now look at this. Q2 has been changed. Q1, see here, flip flop 2 depends upon the Q1. So Q1 has changes from 1 to 0. That means when the Q1 changes from 1 to 0, Q2 is also changed. So Q2 is 0, it changes state to 1. Now this will be a present state. So that is a 1 0. Now this Q1 will changes its state. Why? Because it's connected to 1. So this, now Q1 changes from 0 to 1. So Q2 will not change, because to change Q2 I must require Q1 should change from 1 to 0. So this state will remain as it is. Now this will be the present state at a third clock pulse. What should be this? This will change from 1 to 0. Now what happens to the Q2? Q2 will also change. Look at over here. The Q1 changes state from 1 to 0. At that time Q2 changes. So Q1 changes from 1 to 0. So Q2 is also changed. Now this will be the, look at over here. Why it's called the up counter? 0 0 initial state. It will 0 1 1 0 1 1 again 0 0. When you go the fourth clock pulse, it will be in the repeated state. So 0 1 2 3 0 1 2 3. That's why we call it as a up counter. Now for you I had put it the down counter also example. It's a 2-bit down counter. What do you mean by down counter? Again 3 2 1 0 3 2 1 0 3 2 1 0. This is what we call down counter. Again, what are the things I had changed from the previous circuit? Instead of Q1, I had took the Q1 bar input to this flip flop. Now what you can able to comment, when this Q1 and Q2 change its state, look at the flip flop 1. These are the negative edge trigger. So flip flop 1 changes its state when the clock input changes from 1 to 0. That means if the clock input changes from 1 to 0, the Q1 state will change. What about the Q2? Q2 will change the states when Q1 bar changes from 1 to 0. Why? Because the negative edge of trigger and Q1 bar is connected to the clock of the flip flop 2. That's why Q1 changes from 1 to 0. At that time the flip flop, the Q2 will change its states. So let us take the example. At the first clock pulse, both the inputs present states are 0 0. But what about the next state? So Q1 will change the state. Why? Because the J and K are connected to the 1. And when both are connected to the 1, it will work on a toggle state. That means previous state is 0, next state will be toggle, that will be 1. So this is 1. Now the Q1 changes from 0 to 1. What happens to the Q1 bar? That will change from 1 to 0, and Q1 bar changes from 1 to 0, Q2 also changes. So Q2 changes from 0 to 1. What should be the next? This will become over here. That is nothing but a present state. Now it will be the present state of a flip flop. Now this will be the present state. Again, Q1 will change from 1 to 0. If Q1 will change from 1 to 0, what is the condition for a Q1 bar? From 0 to 1. And when it happens, the Q1 bar changes from 0 to 1, the Q2 will not change. The Q2 will remain as it is. Now this will be my present state at the second clock pulse. Q1 first changes from 0 to 1. Now if the Q1 changes from 0 to 1, what happens to the Q1 bar? It changes from 1 to 0. At that time Q2 also changes. So this will change from 1 to 0. Now at the third clock pulse, this will be the present state. Again this will change from 1 to 0. Because this is the present state. What should be the next state? It's a toggle. That's why it's called a toggle. Now from Q1 changes from 1 to 0. So what should be the Q1 bar? 0 to 1. So Q2 remains as it is. See, this is down counter. 3, 2, 1, 0. Again, when you go to the fourth clock pulse, again you will come to this state only. That is a 3, 2, 1, 0, 3, 2, 1, 0. This is the next state. Now when you go to the fourth clock pulse, this will be the present state 0 0. So it will be 3 2 1 0 3 2 1 0. That's why we call it down counter. Okay, now for your example I took one, that is example of an binary down counter. Okay, I have the flip flop 1, flip flop 2 and flip flop 3. This is the 1, this is a 2 and this is a 3. See, this is a 3-bit counter. So how many possibilities we have? 0, 1, 2, 3, 4, 5, 6, 7. Again 0, 1, 2, 3, 4, 5, 6, 7. It's a 3-bit count. So it can go up to 2 raised to 3, that is 8. So 0 to 7, again 0 to 7. It's a down counter. So 7 to 0, 7 to 0. Okay, I have over here, this is the QC bar, QB bar and QA bar. This is the clock has been given to the flip-flop 1. So when this flip-flop 1 will change its states, when the clock changes from 1 to 0 or 0 to 1. This is a positive edge of trigger. So Q1 changes states from 0 to 1. Okay, so Q1 change plus QA will change. QA will change when the clock input changes its state from 0 to 1. What about the flip-flop 2? QB changes states when QA bar changes from 1 to 0. Why? Because a QA bar is given. Okay, QA changes from 0 to 1, that's okay, but this is QA bar changes from QA changes its states from 0 to 1. So QA bar changes states from 1 to 0. Okay, so initial state QC, QB and QA, that is 0, 0, 0. Now first QA changes states 0 to 1. So why? Because J and K are connected to the logic 1. So it will be toggle state. So 0 changes to 1. So 0 changes to 1. That means if QA changes from 0 to 1, QA bar that should change its states from 0 to 1, because the QA bar will change from 1 to 0. That means this should be a negative edge of trigger. So that is my mistake over here. This should be a negative edge of trigger. Okay, now it should be clear. That will be clear now. So QA bar changes states from 1 to 0. At that time only this clock pulse will change its states. So this QA has been changed from 0 to 1. So QA bar will change its state from 1 to 0. So it will change B and C also, because the QB bar also will change from 1 to 0. That's now this will be the present state. This change will change from 1 to 0. Now QA changes from 1 to 0. That means QA bar will change from 0 to 1 again. So QB will not be changed. If QB will not be changed, QC will not be changed, because QB has changed. It did not change its state. It always remains from 1 to 1. So this is also remains 1 to 1. Now this will be a present state. This will toggle from 0 to 1. Now QA changes from the 0 to 1. That means QA bar will change its state from 1 to 0. That means if it is 1 to 0, this state changes from 1 to 0. If QB changes from 1 to 0, but QB bar will change from 0 to 1. So this will remain as it is. There will be no change in this, because the QB has changed from 1 to 0. To change the state of QC, your QB bar should change from 1 to 0. But here the QB has changed from 1 to 0. So QB bar will be changes state is from 0 to 1. Now this will be the present state. This value will change. So that is a 0. It changes from 0 to 1. What about the QA bar? 0 to 1. So the QB will remain as it is. And the QB doesn't change. So QC will always be as it is. Now this 0 will convert into 1. And now QA changes from 0 to 1. What about the QA bar? That is 1 to 0. That means QB will change its state. So it had changed its state from 0 to 1. QB changes from 0 to 1. What about the QB bar? 1 to 0. That means QC will also change now. Are you waiting or not? This will be a present state now. This value will change 0. Why this value always changes? Because the J and K is connected to the logic 1. So what might be the present state? It will go changes to the next state. So this changes from 1 to 0. So your QA bar has not been changed. Okay, so these two both remain same. This will be a present state. Now again, look at over here. QA changes from 0 to 1. So QA bar changes from 1 to 0. Which flip-flop output will change? QB will change. So this will change to the 1 to 0. When QB changes from 1 to 0, what about the QB bar? 0 to 1. So QC will not change. It remains as it is. That is last condition. 1 to 0 does not change, because QA bar should change from 1 to 0, and that condition is not possible. So 0 0 0. And take the present state again, it will be like 1 1 1, and this will be in the repeated loop. So 0 to 1 and 0 to 1. So this is nothing but a down counter. Now you have to create a 3-bit binary up counter in a homework. So that you will get an idea, and if you have questions you can message me personally. Just I can call you and I explain you that things also. Now these are the two most MP counters we have. We call it a 4-bit ring counter. Why we call it a ring counter? Look at over here. All the flip flops are going. Why I use the D flip flop? Because I need to store the bit element. Is it synchronous or asynchronous? Synchronous. Why? Because each and every clock is connected to the common clock. That's why we call it synchronous counter. D flip flop. Output of first flip flops is connected to the input of D. Another B is connected to a C in flip flop. C output flip flop connected with D flip flop. And last flip flop output is again connected to the first flip flop. So that's why due to this loop we call as a ring counter. Now let us like this is a synchronous counter. Previously we had learned about the asynchronous counter. This is so in the asynchronous counter we have present state and the next state. But in this we don't require present state and the next state. Okay, that means 2 cycles we don't require because it's a synchronous counter. So it depends upon the present states only. Now look at over here. Initially QA output I put it at a 1, QB output I put it 0, QC output I put it at 0, and QD output I put it at 1. Now when the first clock pulse come, D, what is the truth table for a D? It will get output to the same state. Okay, just it will forward to the next block. Now this is the logic 1. Okay, now this is the logic 1 will come from this input. So each and every bit will move in the next step. So this will go here, this will go here, this will go here, and again this will come back to this input. Are you getting? So when the first clock pulse comes, this bit will move forward in this direction, and last will bit come over here. So it will be like here. This will come over at this position QA. This will come over here. This too will come over here. When the third clock pulse comes, this will come over here. Okay, there is a 0. And this will come over here 1 1 0. Again QD will come to the QA 0. This QA will go to the QB, QB will go to the QC, and again this one. Again the QD will go over here 1 0 0 and 1. So this will be in the ring counter. That's why we call as it's a kind of a ring counter we have. Okay, this was just an example like what we have. So it's nothing but a transmission of a simple line. Okay, so look at this 1 0 0 1. So this is what. Okay, so QA equal to 1 0 0. They took the more bits. So as per diagram I took the different. This is how the bits had been transferred from each and every clock pulse. See, transaction always takes place in the positive edge of trigger because the flip flops are positive edge of trigger. Are you getting? Okay, this was about the ring counter. Next we have a Johnson counter. What is the difference between ring counter and Johnson ring counter? Here in the ring counter, the last QD has been sent to the QA or the D input. Here inversion, that is a QD bar has been sent to the input of a first flip-flop. That is what the difference between ring counter and a Johnson counter. Look at initially all the flip-flops are 0. QA, QB, QC and QD are 0. What about the QD if 0? What about the QD bar? That will be equal to 1. That means at the first clock pulse comes, what happens? This is already had been sent to the input. That means this will go inside to this flip-flop. So this will be 1 and these are 0, 0. Now this QD bar, QD is 0, QD bar equal to 1 and that next clock pulse comes, this will be 1 and rest of them are shifted inside the flip-flop. What about the QD bar? Again the 1, 1, 1, 0. Again the 1, 1, 1 and 1. When this flip-flop is 1, what is the value of QD bar? 0. That will go to the input 1, 1, 1, 0, 1. Sorry, this will be 0, 1, 1. This will be 0, 0, 0, 1. So this is nothing but a simple. That is what we call the Johnson ring counter. What is the difference between ring and Johnson ring? In a ring counter, QD will go to the input of a QA flip-flop. But in Johnson counter, the QD bar will go to the input of the another flip-flop. So thank you. This was the introduction about the ring counter and the Johnson ring counter.